So these are the sort of important predecessors historically, Wilbur's work and the Bardia-Kono work, that and everything that's happened in sort of Seiberg-Witten theory in the past few decades. So the content of today's talk is another theorem of this sort, but just it's a different example. I want to consider manifold, which is a connect sum. It's actually a connect sum of two identical pieces, and each of those pieces is a K3 surface. On a connect sum, as I'll explain, there's a preferred self-diffeomorphism. Diffeomorphism or diffeomorphism up to isotopy, perhaps I'll slightly blur the difference here. I think if it's a self-diffeomorphism of Z, and it's a generalization of the two-dimensional self-diffeomorphism of a surface, which is the Dane twist. And I'll carry on calling this the Dane twist, even though we're now in 4 dimensions. And this is supported in the neck. And I'll draw a picture and explain in a moment. Then the theorem states that this this delta is not isotopic as a diffeomorphism to the identity. This diffeomorphism is isotopic to identity in the topological category for the same reasons that's going on in earlier work. For simply connected four manifolds such as Z, being topologically isotopic to the identity is exactly the same as acting trivially on the homology of the four manifold. It'd be rather evident when I draw the picture that this delta acts trivially on the homology of Z. So while the theorem says it's not isotopic to identity as a diffeomorphism, it certainly is as a homeomorphism. So let's pause to talk about Dane twists. So with two manifolds, we think of Dane twists around curves in the two manifold, and they can be either separating or non-separating. A connect sum is the sort of separating case, but that's the case that's I'm thinking about and is relevant here for me. So here's my connect sum, and being a connect sum, it contains inside the middle where the connect sum is made a cylindrical piece. If this is an n-dimensional manifold, 0, 1 times the n-1 sphere sits there as a neck in the middle. The Dane twist is a self-diffeomorphism, this connected sum, which is the identity outside the neck. And what it does in that neck there, it twists the neck. On this cylindrical piece, it has the form delta of TS. It's given by rotating by T the point S. Now, what is the notation there? This is rho there is a path from 0, 1 into the group of, might as well be the group of rotations of the n-dimensional sphere, SON. So this is a rotation of the sphere. This is a point on the sphere. And this rho is a closed loop in SON. Pi 1 of SON is non-trivial. This could be a generator of pi 1. So arcs which run straight across the neck, as in the typical Dane twist picture. In 2 dimensions, this is the picture. It's not really a necessarily very accurate in higher dimensions. All the homology, the second homology of the connect sum of 2 K3s is all on this side or that side. It's clearly left fixed by that such a diffeomorphism. In dimension 2, as long as both sides have non-abelian fundamental group, you can see that this Dane twist is not isotopic to the identity by just looking at what happens to the free homotopy classes of loops on the manifold. Once we're talking about simply connected manifolds, or even once this neck is simply connected, the fundamental group doesn't tell us anything. As I'll begin to say slightly more broadly in a minute, it's actually quite puzzling to try and think about other cases and try and figure out when this when such a Dane twist can be non-zero. I'm going to just redraw that picture here and connect this to a sort of sub-question, as it were. So that the Dane twist diffeomorphism is kind of supported in here. And if this side is x1 and this side is x2, let me look at this piece, x prime. So that's all of this side and including the neck up to this boundary here. So that's really just a copy of x1 minus the interior of a ball. Right? That's what that is. If that Dane twist on this closed four manifold is not isotopic to the identity, then it should certainly not be isotopic to the identity just as a diffeomorphism of x primed fixing the boundary. If I can isotopic to the identity as a diffeomorphism x primed fixing this boundary, well, I can isotopic to the identity through diffeomorphisms of the connect sum by just extending it by the identity, that isotopy over this side. So let's just think about this this story instead. Let's start with just the manifold with boundary that I get from a closed manifold X by removing a standard ball. And at the moment, perhaps we're still in any dimension. And then there's a diffeomorphism supported in a collar of the boundary, which is, if you like, the Dane twist around a sphere, which is sitting inside that collar. So that's a diffeomorphism, or perhaps if you prefer, an isotopy class of diffeomorphisms. it's a diffeomorph. I write this notation X, that means rel boundary. So this means diffeomorphisms of X primed, fixing pointwise the boundary of X primed. So the boundary of X primed here is an n-1 sphere. So this is slightly simpler, if you like, than the connect sum of two manifolds. This is just a single manifold we're dealing with here, and it's a great question to ask. For which closed smooth X is delta X non-trivial. That is to say, not isotopic to the identity in this diffeomorphism group. So in dimension 2, this Dane twist along the boundary is always non-trivial as long as the fundamental group is non-abelian. So that's except for the sphere and RP2, I think I'm right in saying this delta X is always a non-trivial element of the mapping class group. For a hyperbolic 3-manifold X, this delta X again is always non-trivial. It's I'm not sure what the minimal proof of that is, but it certainly follows from work of Gabay and others on sort of stronger 3-dimensional versions of rigidity. That's hyperbolic 3 manifolds. For higher dimensional manifolds, like n-1 connected 2n manifolds for n bigger than 2, so 3 connected 8 manifolds, for example, and other such things. This is actually very well understood, and that's a lot of it goes back to the general theory of wall, but this particular question is very much addressed in a later paper by Craig. For dimension 4, this exact question was asked very explicitly by Jeffrey Jan Siracusa in a paper on the diffeomorphism group of K3, essentially, in many ways. And to come back to my introduction comments, this is in a very slightly different formulation, the question that was answered for the K3 surface by Bavelia and Kono. So this question was answered in the negative. Delta K3. This isn't actually the wording of their theorem at all, but it's eventually equivalent. This diffeomorphism is non-trivial in pi 0 of the diffeomorphism of X primed L boundary, where X primed is K3 minus a ball. And that's 2019, I think. generally, we know very little about this question, I think. From Jan Feng's talk a couple of weeks ago, you can deduce the same result for a slightly more difficult case, which is not just the K3 surface, but the K3 connect sum S2 times S2. So corollary of his result. If you took a connect sum of two K3s, I don't know the answer to this question. I don't know the answer to this question if X is a smooth sextic surface or just about a huge slew of examples. If X is simply connected, and not spin, then this delta X is trivial. That's true in any dimension, and it's and perhaps why that is might become clear later in my talk if I do a good job. To think about this question, it's helpful to think about it in a few different ways. And although this result here is proved by Borrelio and Kono using Seiberg-Witten theory, what I want to talk about today is a very slightly different proof of the same result, also using Seiberg-Witten theory, but just with a setup which makes it easier to go back to the Dane twist on a connected sum. If I just bring back the previous bit of paper here, there's the result, which I've just hidden, is a statement about the non-triviality of a self-diffeomorphism of this manifold rel boundary. So that's a self-diffeomorphism which I can think of as being supported away from the boundary, the identity on the boundary of this manifold. The theorem, scrolling back one further page, talked about a connect sum of two K3s and the statement that a Dane twist in the neck was non-trivial. So the strategy to prove that connected sum non-triviality theorem is write down a proof using Seiberg-Witten theory that this self-diffeomorphism is non-trivial. A slightly different argument than Borrelio and Kono's, but sort of wielding the same tools, and set it up in such a way that from the non-triviality here, we can deduce the non-triviality here. And deducing the non-triviality here, I mean, it's kind of what the picture says. It's like a gluing theorem. It's in gauge theory. I've got to glue on this trivial piece and see how the gauge theory calculations are changed. The actual tools we use in gauge theory, as I said, Seiberg-Witten equations, the first refinement of the statement we use Seiberg-Witten equations is to say that we use the homotopy refinements of the Seiberg-Witten invariants, which were introduced by Bauer and Furuda. And as a second refinement to consider these Bauer-Furuda invariants of four manifolds, when instead of a single four manifold, we have a family of four manifolds. And such invariants of families have been studied by other authors. I think they're first studied by Shu and later by Simic, and then they appear in the work of Kono, Braglia, and others since. I wanted to just try and give you a feel for non-triviality of this boundary Dane twist by reformulating it a few different ways and perhaps thinking about about some reformulations. So we're interested in pi0 of this diffeomorphism group of this manifold X primed Rel boundary. X primed is a closed manifold minus a ball, the boundary is a sphere. Another way to say this same group is pi1 of the classifying space, it's pi1 of B diff, X primed B. So pi1 of the classifying space, that's classifying bundles over the circle. So we can think of bundles over a base B. In this case, the base is the circle S1, and the fiber is X prime, this manifold with a sphere as its boundary. And the structure group is just diffeomorphisms of X prime, which pointwise fix the boundary. But removing a ball and fixing the boundary pointwise, once you have a smooth structure, is no different to sticking to your original closed manifold X. And instead of cutting out a ball and framing the sphere there, we can, let me do a thinner pen. Let's take a base point X and just think about a framing of the tangent bundle, so a oriented basis at that point. So this is some theta, which is in the frame bundle at the point X of our manifold capital X. So we can think of families of such objects over the circle. So we've got a picture here now of the base, which is the circle. And we've got a family of X's with a family of framings at the base point X. This family has a monodromy, and that monodromy will be an element of the diffeomorphism group of X. The diffeomorphism of group of X, which preserves the framing theta, so it preserves the base point and maps this frame theta back to itself. And this is just, this has the same homotopy groups as removing a ball and fixing the boundary pointwise. So when interpreted as a family, what is this? So in here, or in the component group of here, is this Dane twist on the boundary. What family does that correspond to? That corresponds to a family of manifolds over the circle where X is not moving, it's just a trivial family of X's. This base point, little x, is not changing. All that's changing is the frame, which is, as we go around the base, the frame is rotating. So this is a non-trivial family of x's with framed base point. Framed as in sense, framed with a tangent space there. I mentioned the work of Craig, a sort of high dimensional case. If you dig into his paper, there's a very nice example. What happens if X is a higher dimensional manifold, e.g. A 3-connected 8 manifold, just for concreteness. Well, you can look at the total space of this fiber bundle. It happens to be a product in this case, S1 times X. But it's a smooth 9-dimensional manifold. And inside that smooth 9-dimensional manifold is a circle. Again, this trivial family of X's. But it's a framed circle. And it's sort of framed in a twisty way. It's not the trivial framing of this circle. So if you want to recognize that this family is a non-trivial family, that delta X is not isotopic to identity, you could forget the fibration structure and say, okay, let's just think about the total space, a 9-manifold containing a circle, a framed circle, and try and identify whether that 9-manifold with a framed circle is isomorphic to the product case. And being good topologists, as soon as we see a manifold with a framed circle in it, we straight away do surgery on the circle. So there's this 9-manifold S1 times X. There's this curve in it, which is just S1 times X, and it's framed in an interesting way. And we do just traditional surgery. We take out a new tubular neighborhood. So we're going to state N minus a neighborhood of gamma. That leaves as its boundary S1, in this dimension, S1 times S7. And we just do surgery. We glue in D2 times S7. Using the framings that we have here. Something really neat happens if X is a homotopy sphere. I mean, because then this new manifold, surgery on N, is also a homotopy sphere, but of one higher dimension. So this is sort of known recipe for producing a 9-dimensional homotopy sphere. There's one exotic 8 sphere. If you do this construction with the exotic 8 sphere, this thing is an exotic 9 sphere. In particular, it's a non-standard manifold. So that means that this was a non-trivial. This was a non-trivial family. So that example due to Craig, I think, it says that delta X is not isotopic to the identity if X is an exotic 8 sphere. That 9-sphere that you get is also, if you're a 4-dimensional topologist, then you might recognize something about that 9-sphere, that it's actually, that exotic 9-sphere is obtained from the standard 9-sphere in this construction by, it's just how you glued in this D2 times S7. So it's actually obtained from the standard 9-sphere by the sort of 9-dimensional version of the Gluck twist. Gluck twist, you take the neighborhood of a 2-sphere in S4 and glue it back a different way. That's sort of what's happening here. This framing is exactly the sort of Gluck twisting. What's slightly interesting is that the S7 here, this in the standard 9-sphere, this is the standard S7, and you're doing the Gluck twist on the standard S7. So how are you obtaining something exotic? It's the standard S7 in the 9-sphere, but it's parametrized in a different way. It's parametrized by an exotic diffeomorphism of S7. If you're going to talk about 7 spheres in the 9-sphere, you can consider them as just submanifolds, but then you can consider how they might be parametrized by the 7-sphere. Whereas with classical knots, that's just an orientation question of which way do you go around the knot. For a 7-dimensional knot in 9 space, it's how do you parameterize the 7-sphere, those exotic diffeomorphisms of the 7-sphere. To return to dimension 4, let me sort of redraw that picture up there. The base is S1. The fibers now are K3 surfaces. And we have this rotating framing. It hasn't started to rotate yet in my picture. Rotated framing at this base point. Maybe that's X. The K3 surface is spin. It has a unique spin structure. But if I want to put a spin structure on the total space, or slightly more appropriately here, if I want to consider a fiber-wise spin structure on X, that's a smoothly varying spin structure on each fiber. I've got 2 ways to do that. On the fiber, there's this unique spin structure, but there's H1 of the total space with coefficients in Z2, which acts on the set of spin structures. To pick out a particular spin structure on the family, I can use a framing at this base point. The 2 different spin structures on the total space, the 2 different fiber-wise spin structures on the whole guy, they're distinguished by how they look in a tubular neighborhood of this curve gamma. This framing has just trivialized the tangent bundle in the neighborhood of gamma. So once you trivialize the tangent bundle, you certainly automatically got a lift to spin. So there's there's two spin structures for the family. That's fiber-wise spin structures on these K3 surfaces. There's sort of the product one, S0, and there's the non-trivial one. This is the product, and this is not a product. A spin structure is exactly what we need to set up the Seiberg-Witten equations. And a family of spin structures on a family of four manifolds is what we need to set up the Seiberg-Witten equations on a family of four manifolds. We could use spin C structures, but I'm here thinking about just the spin case. So to start with a single K3 surface, Seiberg-Witten theory associates to this, once you've chosen a Riemannian metric, a nonlinear map between two Banach spaces, Hilbert spaces, if you like, W plus of X and W minus of X. These are Banach spaces, but the Bauer-Ferrada idea is to replace these by carefully defined, appropriately defined large finite dimensional subspaces. That's lowercase SW from some Roman S plus of X to Roman S minus of X. And what their construction depends on is that just as the Seiberg-Witten equations have beautiful compactness properties, these finite dimensional approximations have compactness properties too, which this isn't quite true, but you can think of it as just saying that this is going to be a proper map between two linear spaces. More precisely, it's proper over the inverse image of some large ball here. If you've got a proper linear map, proper smooth map between linear spaces, or if you like, compactifying just a map between spheres, it has a homotopy class. Because we had to choose how big the finite dimensional approximation was, we have a map between spheres which is well defined up to stabilization. So we have an element of the kth stable homotopy group of spheres, where K is the fiber dimension, so dim W plus X minus dim W minus X. If you carry this out for K3, if you take the smallest W plus and W minus that seems feasible, you actually sort of get the right answer. In Bauer-Ferrada say you have to take large enough ones, but actually small is big enough here. And what is the right answer? For K3, you can legitimately and without too much error think of the Seiberg-Witten map here as being a map from C2 to R3, which is the cone on the Hopf map. The Hopf map from the 3-sphere, the unit sphere here, to the 2-sphere, which is the unit sphere here. In terms of a complex vector, this is also this is a Hermitian matrix, phi star. Take the traceless part. This is a traceless 2x2 Hermitian matrix, and there's a chronically the same as R3. How do these arise? This C2 is at least for the standard metric on K3, this is the kernel of the Dirac operator. And this is the kernel of another operator, or it's the co-kernel of the operator little d plus. This is the self-dual harmonic forms H2 plus of X. Index of the Dirac operator is 2, and that's what this map is. What is the fiber of this map? So the Pontryagin-Thom construction says we can think of this stable homotopy group as just the fibers of such maps, which are framed one manifolds. And a framed circle is the fiber. Remember, this is the suspension of the Hopf map. This circle is one of the fibers of the Hopf map. And it's the framed circle with the framing that does not bound. And this is the generator of the stable one stem. So that is, in its most primitive form, the Bauer-Froude invariant for the K3 surface, and it's this non-zero guy. But now let's take a family of K3 surfaces over the circle and do this over the circle B. B is the base here. And this fiber bundle, its fibers are going to be these K3 surfaces. And remember, there are two possible spin structures in families, or in this family of K3 surfaces. There's S0, which is the product, or the interesting twisted one, S1, which corresponds to this Dane-twist situation. Choose one of those either way. Well, instead of a Banach space W plus, we'll have a Banach vector bundle associated to X and be a fiber bundle over B. And instead of a Banach space W minus, we'll have a Banach vector bundle over the circle. And here, instead of just a map between Banach spaces, we'll have a fiber-wise map of Banach spaces. This is a fiber-preserving map, the Seiberg-Witten map. In the simple case of the product S0, if we take finite dimensional approximations here, whereas before for W plus, we just got C2. Now we've just got C2 times the base, B, the circle. And then we've got the lowercase Seiberg-Witten map, the finite dimensional approximation, and it maps to, well, it's a fiber-wise map, it maps to R3 times the base. But there's an important point here. This R3 arises as H plus of X. It sits inside H2 of X as a vector space. But H2 of X is a fixed thing. H plus is just some positive subspace of H2. It's a contractible space of choices to take a three-dimensional positive subspace inside this 319 signature quadratic form here. So in a way that's canonical up to homotopy, this R3 bundle, which is arising as a kernel of D plus, is trivial. So this is really just a map to R3. This side, this is this is for sure C2 times B if I really put the product structure on everything. But if I mess around with the metrics and stuff, this is just a family of kernels of the Dirac operator. And it's important that the Dirac operator in this dimension 4 is quaternionic. Over the circle, any quaternion bundle is not just trivial, but canonically trivial. There's only one way up to homotopy to trivialize a quaternion vector bundle of any rank over the circle. So although initially this is really just some trivial, but not trivialized bundle here, we actually get a preferred trivialization up to homotopy. Anyway, just choosing the whole product structure, we just get this this straightforward map SW, which is just the map we had before, but with this extra B here. This B is a circle, and we'll frame that circle. We won't frame it with a Lie group framing. We'll choose to frame it as the boundary, it's a stable framing as a boundary of the disk. So what is the fiber of this map? It's just still in the C2 term, it's just that fiber of the Hopf map. But now this is happening over the base. So this is now times the base B with a trivial framing. And this is the element 0 in the stable 2 stem. We just multiplied it by this trivial B on the bottom, nothing happened. Interestingly, when we put in S1, this gets twisted in an interesting way. Instead of the product C2 times B, it's a twisted C2 bundle over the circle. Twisted in that the monodromy, as you go around the circle, is -1 on this vector bundle. Of course, -1 isn't a very interesting thing. This isn't an interesting topological vector bundle over the base. But the map SW commutes with the map -1. So there's an interesting, well-defined map here from C2, the C2 vector bundle to R3. This is what we get for the twisted guy. And if you compute the fiber here, it's eta times eta, which is the non-zero element, a non-zero element in the stable 2 stem, which is also Z mod 2. This proves this family was not the trivial family, and this is a sort of reproving of the theorem of Baraglio and Kono, that the boundary Dane twist for K3 is non-trivial. Just to wrap up in the remaining 2 minutes, the original theorem I advertised was about the K3 connect some K3. And for this, we have a connect some theorem due essentially to Bauer, carried out now in a families version. We have a family of K3 surfaces with an interesting family of spin structures on the total space. We have another fixed K3 surface, and fiber-wise, we're just going to form this connected sum. What we have now is a family of closed manifolds, and the monodromy now is going to be this Dane twist diffeomorphism of the connected sum. So to prove the original theorem, we have to compute this Bauer-Froude invariant of this family. The connect sum theorem, which Bauer proved, states that when we form this connected sum, we just get a product. For the original family we just treated here, it was eta times eta was our Bauer-Fruit invariant of the family. And then we just multiplied this by the K3 surface, and the K3 surface was eta. So that went off the bottom of the screen. So what is this guy? This guy is the element in element 12 in Z mod 24, which is the stable 3 stem. In particular, this is non-trivial. So this family of Z's over the circle is a family with a non-trivial monodromy detected by this non-trivial Bauer-Fruit invariant. So that's basically the end of the talk. I think the takeaway is that we have very little tools to demonstrate non-triviality of these sorts of pictures. I mean, Seiberg-Witten invariant gives us occasional Z mod 2s, which we can try and wield. But as I think was already evident from when Danny Wuberman exhibited his first example, it really seems that just as four manifolds themselves are mysterious things for which we have very few useful tools, and we have Seiberg-Witten theory and stuff, but it seems like they just scratch 1 millimeter below the surface of the problem. For sure, I believe that these Dane twists in the non-spin case have got to be much more generally non-trivial than just this case. But apart from K3, homotopy K3, maybe add an S2 times S2, we just don't have the tools. We just have a few Z mod 2 valued invariants to throw at it, which seems like nowhere near enough. There's the work of Watanabe, which to some extent inspired Tom and me to sort of go back and think about these questions, which is a whole other ball of wax for potentially investigating diffeomorphism groups of manifolds. But I will not go there except to say that was perhaps our motivation in starting this project. So thank you.
People can ask questions. I don't think we have so many to overwhelm.
Danny, you're making enough noise that Zoom has highlighted you. But,
no, I was just, well, I do have a question. I wasn't trying to do that. But so are there other examples that one might get by the same technique? You know, when you do this Dane twist along a 3-sphere, of course, you know, you're only just using really just the fact that there's a circle action on that 3-sphere. You're not using the whole SO4 there. So do you know, I mean, there's lots of 4 manifolds, excuse me, that are split along, say, 3 manifolds with ciphered fibered, with that fibered homology series. Does this work, you know, just sort of off the shelf in the same way, that way?
I mean, I tried and didn't succeed. A really interesting 4 manifold, which is decomposed along a Seifert fibered space, is the 4-sphere. And you just take a Seifert fiber space which bounds, for example, a Maser manifold, M, and then you just double it. And you know, so this is I don't know, it's 3, 4, 5. One of them, the first, I'm not quite sure. You know, one of those which does bound a Maser manifold. And yeah, so doubling is not usually very interesting in 4-dimensional topology. So anyway, this thing is uninteresting in the sense that it is S4. But this has, just as you said, a circle action, which is all you really need to construct a Dane twist. So there's a self-diffeomorphism of S4, which is supported in this neighborhood of this interestingly embedded Seifert fiber space. Yeah, so I tried to compute Z-mod 2 valued invariance using Seiberg-Witten of these families, I didn't manage to create a plausible scenario where it could reasonably be supposed that the answer was non-zero. So I don't know. I don't know whether I didn't try hard enough, or this is actually, for some direct reason, actually a trivial self-diffeomorphism, or it's non-trivial, but Seiberg-Witten theory will never show that. I mean, I don't know. I think this is interesting. But yeah, slightly less ambitious already, just inside K3 surfaces. Obviously, as I think you're sort of saying, there's lots of four manifolds containing Seifert fiber spaces.
Yeah, famously, I guess sigma 237 sits in a K3 surface.
Right.
So Peter, Marco asked if there was a stabilization theorem for boundary Dane twists.
Yeah, I tried to find a statement like that in the literature, or to try and deduce it from things I saw elsewhere in literature, but perhaps I'm not the right expert here. But the question is, and for just perhaps to explain to other members of the audience, if you have this manifold, remove a ball, and then connect some with a lot of S2 times S2s, which I think is the question that's being asked. After doing that, can you be assured that the Dane twist near the boundary becomes isotopic to the identity? And yeah, that's a good question. I'm pretty sure the answer must be yes. But it didn't seem to be something I could deduce from off-the-shelf sort of theorems in the literature. As I said, Jianfeng Lin's result implies that when X is K3 and you do a single S2 times S2, that's not enough. That it's still exotic. And you know, more familiar is the case of a closed manifold where we do know the answer to that question. Yeah, I think there must be such a stabilization result, but I just don't know where to find it.
I have a couple of questions. This is Salman.
Hi, Salman.
How are you? And let me say, if you change one of the components, orientation of one of the components, K3 connected some minus K3, do you still have it?
I mean, I think that's just another one of an infinite collection of really good questions which we don't have the tools to answer. So your question is this, yeah, that you're asking about this picture, and I take the Dane twist in the boundary, is that isotopic to identity? I don't know. I do know that the Bauer-Frude invariants, at least in any form that I understand how to use them, don't tell you anything about this example. Yeah, so it's a good question, but we don't know.
I have another question. If you have, does your theorem hold for K3 connected some S1 cross S3 connected some K3? It seems it holds. When you make your prime, your breakdown manifold in two, you can push one side, S1 cross S3 one side. I mean, S1 cross S3s are good manifolds to extend things over. But I'm not sure. I'm making some calculation here. I'm getting contradiction. Because that manifold is a twofold covering of K3 connected some twisted S1 cross S3.
Yeah.
Which is an exotic copy of twisted S1 cross 3 connected some 11 copies of S2 cross S2. So when you take, if you view that way, take twofold covering of that, you get something different. You get S1 cross S3 and 22 copies of S2 cross S2. So I'm kind of puzzling over this during your talk. In one side, I want this to be true when you put S1 cross S3 in the middle, when you're connecting some to K3. It seems it should go through, but then...
Yeah, I think it's another good question which you should leave with our expert audience. I mean, I think going back to the simply connected case, I'm happy to conjecture, for example, that the boundary Dane twist is always non-trivial on a spin 4-manifold with non-zero signature. I mean, I will just don't know about that. I mean, that would be refuted if this stabilization thing works. But that's that at the opposite extreme just shows how little I really know about the question. That apart from this very tiny world where the Seiberg-Witten equations tells me something, I just don't have any a very good feel for this.
Peter, I have a question.
Yep.
Hi. So you mentioned this Watanabe classes. So do you think it's possible to use some of these Seiberg-Witten invariants to actually detect those exotic elements?
That's, I mean, I kind of feel I'm not quite sure what the word is, jealous, inferior. It seems like Watanabe has just a much richer set of invariants than the gauge theorists do for this problem. I mean, so this example, the force sphere split along a Seifert fiber space. Yeah. So Watanabe, although he doesn't do this because at some stage he needs to work with de Wahm cohomology, so he's kind of tied to characteristic 0. I mean, I understand from the experts that Watanabe's work at least points to the possibility of an exotic self-diffeomorphism of S4. And actually, you can describe fairly concretely what that is. This potentially exotic guy. You can use Seiberg-Witten theory to define Z mod 2 valued invariants of self-diffeomorphisms of S4. You can use Yang-Mills also. But actually computing those on this example seemed just really daunting. So that's kind of why we went looking for other examples. I mean, this is not anything like the sort of constructions that Watanabe does, but what's you do what you know best, which is sort of this thing. This thing is clear, if it's non-trivial, it's an element of order 2 in the diffeomorphism group of S4 by 0. which is kind of correct for what you'd guess is going to come out of Watanabe if it sort of properties, and maybe they're the same family, maybe they're not, but you try and compute them using Cybergwin.
So just to follow up on the same question, I think Watanabe constructs non-trivial elements in higher homotopy groups as well.
Right.
Do you have some access to not just pi0, but higher homotopy groups as well?
Well, there's a literature on that. I mean, I didn't really do justice to the existing literature on diffeomorphisms of four manifolds using Cyberg-Witten. I mean, Danny's paper was pi0 of diff. Recent work of Baraglio and Kono is also pi0 of diff. But there's also applications by other authors to higher homotopy groups of diff of four manifolds. I will possibly get it wrong, but I think pi1 of the diffeomorphism group of a K3 surface is non-trivial. There's some, in that sort of range, there's some interesting examples, and maybe for some reducible manifolds. I'm not clearly remembering or didn't revise well enough before the test what those examples are. The construction I described just now, unmodified, certainly defines invariance, non-trivial or not, invariance for families, not just over the circle, but over the two-sphere. Once you get higher than the two-sphere, there's some extra complications because the symplectic group, the quaternion linear group, is contractible until you get to pi3. I don't know how clear that was in my talk, but at some point we used the fact that every quaternion vector bundle of the circle was canonically trivial. Same on the two-sphere, but there's an extra sort of ambiguity from trivializing it on the three-sphere. But yeah, there are existing applications. I don't want to mention the authors because I'll leave someone out, but they're out there. Yeah.
Thanks.
Here's a question. Are there computations for other hypersurfaces of CP3? In ones, I mean.
No. So I mean, well, yes and no. There's nothing. I don't think there's anything about pi0 of diff. I don't think there's anything interesting about pi0 of diff for any irreducible four manifold that I know about. But certainly pi1 of diff and families over the two-sphere. There's a literature and sort of examples of those. Once you get to talking about families over the two-sphere or higher, you have to be a little careful about what you mean by exotic. I mean, if I've got a family of four manifolds over the two-sphere, it's easy to construct interesting families, but then realize that they are non-trivial for rather elementary reasons, like the cohomology ring of the six-dimensional total space is not standard or something. So I'm not sure I know examples where the fiber is a sextic in CP3 and where it's a homeomorphically trivial but not smoothly trivial. I'm not quite sure whether that's.
But these Bauer-Furuta invariants, are those known for other hypersurfaces?
Yeah, for the zero-dimensional Seiberg-Witten invariant is an integer traditionally. When you look at, if you just take the Bauer-Froude invariants in this rather weak sense that I've defined them, which is just each of those points in the zero-dimensional Seiberg-Witten modular space becomes a framed circle, and you end up in a Z mod 2, which is the framed, which is the stable one stem. Unfortunately, once you're past K3, the integer Seiberg-Witten invariant is usually 0 mod 2. So you have to work a little bit harder to get interesting stuff. And in particular, I don't know how to, this story for the K3 surface, it doesn't, you can't repeat that for, say, the sextic hypersurface in CP3. And the reason is that you lose everything becomes 0 mod 2. So that's the answer. Well, perhaps I can thank the organizers again. It's been nice to just click the heels of my red shoes and be with you in Kansas.
Okay.
I'm happy to answer questions till dinner time, but I don't know what time zones everyone's in.
Well, thank you very much, Peter. We will convene next week at the same time, same format. I'm glad people are meeting.
Thank you, Peter.
Thank you all for being there. I enjoyed giving the talk and hope to see you at future talks from the audience side.